Okay, so I want to go over everything you need to know about electric and magnetic fields. Okay, not everything, but just some things. So first, let's start with your normal electric field. So I have here, you may have seen this before, this is two pieces of clear tape, and if I pull them apart, they become electrically charged. As you see, if I bring them back close together, they charge. I can touch them to this electroscope. Let's see if that works. Now, let's see if I can pick up some paper. Okay, so that does work. Picked up some paper. Okay. One more thing, just a quick, throw that away. This is an electroscope that I made. It's kind of working. I had, you can rub some plastic together and charge it up, but it's really humid right now, so I'm going to use this little wand, and you can see. So these leaves all get the same charge, and they repel, and then I can discharge it. Let's charge it back up. Discharge it. There you go. Okay, so this is static electricity that you've been thinking of. Okay, and I dropped my electroscope. So here's what we have. We have what's called the Coulomb field. If I have a positive electric charge, it creates an electric field that radiates outward. A negative charge points inward. And here's an important one, the dipole. A dipole is a positive and a negative charge together, and we get this special shape of a field. Okay, so that's kind of important. Okay, let's look at one other example of a Coulomb field. Not a Coulomb field, but another important point of electric field. Can you see that? I think you can see that. Okay, so this is a battery hooked up to a bulb, and when I turn it on, the bulb glows. Okay, so in order to have, we actually have another kind of electric field right here, because here the battery creates an electric field in the wire that goes in the direction of the current. Okay, so if there's an electric current, then there is an electric field in there too. But also, let's look at this. If I put this compass right, and this is just a terrible little compass, if I put this right under the wire, can you see that? Let me zoom in. Okay, so there's my compass. Watch the compass when I turn on the battery. Can you see that? Let's get a little bit closer. Right there. Can you get it? It's not moving very much. Let's see. Here, one more try. Okay, let's do it one more time. This time I'm going to short out the wire. Sorry for the camera. Okay, so let's just bypass this. We'll get a much higher current, and you should be able to see it better this way. Okay, one more try. Okay, can you see that? There it goes. Okay, so an electric current also makes a magnetic field. Notice how I prepared these boards for you beforehand. Okay, so here is what we have with the magnetic field. So if I have a wire with a current going this way, it makes what we call curly, I didn't make this up, but I like it, a curly magnetic field. So a curly magnetic field essentially makes circles around that wire. If the current was coming out of the page right here, then the magnetic field would make this pattern. If the current was going, we use a dot to represent an arrow coming out, because it's like looking at an arrow. And if you look at the back of the arrow, it looks like feathers, so we put an X. So this is a current going into the board and a magnetic field going in this pattern. Okay, and this is a curly field. You can calculate the curly magnetic field due to a short segment of wire. With this equation, you have a magnetic constant, you have the current, you have a short length of wire, and then R is the distance from the wire to the point you want to find it, and that's R cubed. And that's a cross product, but don't worry about that. Also, if you have a loop of wire, so here I have current going around this way, it makes a magnetic field that looks like that pattern. And that looks exactly like, or pretty close to, the pattern of the dipole field for charges. So we can make those two look the same, okay? But we cannot make, I cannot make a magnetic field that looks like this. And that is because we don't have magnetic monopoles. You can never have one magnetic charge by itself. We can make a dipole, see, dipole, but not a magnetic monopole. Okay. Okay, so next, let's look at the following demo. So here I have a galvanometer. This measures very tiny electric currents. And then here it's connected to a coil of wire, and that's it. So what happens if I take a very strong magnet and I move it into that coil? So watch the galvanometer. I hope you saw that it moved. Let's move this down a little bit. That's better. Okay, so the galvanometer did indeed move. But notice here, it's not because of the magnetic field. It's because of a change in magnetic field. Right now, I have a very high magnetic field going through that loop of wire. It's multiple loops. And there's no current. So watch what happens when I pull it out. Remember when I put it in, the needle went that way. Now the needle goes the other way. It's a change in magnetic field that creates, in fact, it's creating a curly electric field. Okay. Now I can do this a couple ways. I can pull it out. I can push it in. I could flip the magnet over. That would do it. I could flip it over again. It goes the other way. So it's a change in magnetic field. I could also move the coil. Watch this. Okay. So I can do a whole bunch of ways to create a curly magnetic field. And here's what we have. So this is Faraday's law. So the first thing we want to deal with is the idea of flux. So flux tells us how much magnetic field passes through a particular area. Okay, I dropped my piece of paper. But let's suppose that I have this area. And see, it even says area on there. And suppose it's raining. So it's raining straight down like this. So how much rain hits that area depends on three things. First, it depends on how fast it's raining. Then it depends on how big the area is. And finally, it depends on the angle of the area. If I rotate the area like this and it's raining like this, no rain's going to hit it. The maximum rain's going to hit it when they're perpendicular. Okay, so it depends on those three things. And magnetic flux also depends on those three things. It depends on the strength of the magnetic field, the size of the area, and the angle between the area and the magnetic field. Now here's a small point that's difficult. If I have an area like this board, the angle is measured from a vector perpendicular to the area and the magnetic field. So if I have the magnetic field going straight perpendicular into the board, theta would be 0. Okay. If I have the magnetic field in the same plane as the board, theta would be 90 degrees. Okay, so that's that angle theta. So if that's how we calculate flux. So flux is the Greek letter phi. It's a scalar value, be a cosine theta. If I change any of these things, I will have a change in flux. And here is Faraday's law. A change in flux over change in time gives you an electromotive force of voltage. And just to remind you that if I have a constant electric field over some length, then I can get a voltage. Okay, that's not always true because it can change. But I just want to give you a connection between EMF and electric field. Okay, so you get a voltage by changing the magnetic flux. So this is actually a way to create a curly electric field. So suppose I have some magnetic field inside a loop. I turn it off. I change the actually I have to turn it. Change would be, I'm trying to make sure, well, if I change it, okay, because I don't want to get it wrong, then I make an electric field, a curly electric field. And if there's a wire there, that curly electric field makes an electric current. This is Faraday's law. Okay. Now, Lenz's law tells us the direction of this electric field. It says that the direction of the electric field, if it made a current, would make a magnetic field to oppose the change. And I'll show you an example of that. So let's look at a couple of demos. Okay, let's get rid of this. Let's get rid of this. And let's look at this, because this is pretty cool. Now this, I like to use simpler demos, but this is a coil of wire hooked up to the AC outlet. And so because it's alternating current, this makes a changing magnetic field all the time. Now here I have a coil of wire with an LED. So let's put this over here. Okay, and I'm going to turn it on. Hopefully you can see it. So there's no battery or anything. It's just connected to this. So there's a changing magnetic field in this loop, and that induces an electric field, and that makes a current that lights this up. Now the LED actually turns on and off because it only lights when it's going one way. So that's a good example. Now, since I have this out, I'll do my other favorite demo with this. Here's a plain copper ring, and if I place this on here, I turn this on. Let's just see what happens. Watch quickly. There you go. So in this case, the changing current makes a changing magnetic field. That changing magnetic field induces a current in the loop. That current in the loop creates a magnetic field, and those two oppose each other, so it repels it and it pushes it up. So this is a ring launcher. Do it again. Isn't that cool? Okay, let's put that up. Let's do my other favorite. This is a tube of aluminum. Okay, and aluminum is not ferromagnetic. So if I take my strong magnet, it doesn't attract. It doesn't stick. But if you take this and you can't feel it, and you move it, you can feel some interaction. Okay, so let's do this. I'm going to take my magnet and I'm going to drop it down here. And there's plenty of room. See, it's got plenty of room. Okay, so here we go. Check that out. You can't really see it. Let's see if I point down. There we go. So what's happening here is that as the magnet moves down, we have changing flux at different parts of the tube that creates an curly electric field, which creates an electric current, which creates a magnetic field to oppose this. Okay. How about another example? This is a hand crank generator. So if I turn the crank, it lights up. So how does this work? I'll show you. If I disconnect this and instead take a battery, now watch what happens as I connect the battery. So this inside here is an electric motor. And an electric motor has a coil of wire that you run current through, and it interacts with some magnets and it turns. But if I do the opposite, if I turn the coil of wire in the magnetic field, I generate a curly electric field, which creates an electric current. Okay, so that's how a hand crank generator works. Just to show you, I won't really show you, I'm just going to tell you. This is another magnet and a coil of wire in there. It's a speaker. Okay, so a speaker does the same thing. If you run current through that wire, then it makes a magnetic field that pushes this cup and it makes some sound. But if you take these two wires and hook it up to an audio input and then you talk into this, it will record. Okay, so a speaker can be used as a microphone. It works the same way. Okay, and in fact, you could hook up a motor. You can hook up a motor to a audio source, and you can actually sometimes hear it too. So that's kind of cool. Okay, so that's your introduction to Faraday's Law.